Okay, so welcome to this DaSCI seminar about autonomous driving research. First of all, I want to thank Professor Antonio López for very kindly accepting our invitation. Antonio López is the principal investigator on autonomous driving at the Computer Vision Center and associate professor at the Department of Computer Science of Universitat Autónoma de Barcelona. He has a long track career research at the intersection of computer vision, simulation, machine learning, driver assistance, and autonomous driving. And today his talk will focus on how to minimize data labeling efforts, including the use of simulated data to support the training of visual models, the development of self-labeling procedures, as well as exploring non-standard paradigms for autonomous driving, such as end-to-end driving by imitation learning. Again, thank you very much for accepting our invitation, and whenever you want, the floor is yours.
Okay, thank you very much, Pablo, for the invitation. For me, it's a pleasure because then I know more places around, and that's good for me also. So today I have put together a bunch of slides for presenting you some of the works that we have been doing in the last years, and also it's a way for people that don't know us, that you can know what kind of research we do. So let's start. 1 second. Okay. Just let me start by saying a few words about the Computer Vision Center. We are in the campus of the Autonomous University of Barcelona, the UAB. The UAB, in fact, is one of our, let's say, bosses. There are a couple of them, and one is the Universitat Autónoma of Barcelona. The UAB is not really in the center of Barcelona, it's in the outside area, and we are close to the AP7, which is very famous highway that connect France to the rest of Spain. And also we have very close to us the Alba synchrotron that probably some of you may know about it. And well, this is where we are. And basically the mission is to do research, to do technological transfer, to do training of students, all kind of students, and of course outreach to let the society to understand what kind of applications can be achieved by computer vision. I think, I don't remember, probably we opened this center more than 25 years ago, 27 I think. I was among the founders of this center. Yeah, here are the numbers, 27 years, and along these years we have been doing publications, many PhDs, also many projects with companies, and even a bunch of spin-offs. And of course, because maybe you are interested, the people in this talk, and in this talk, we used to accept undergrad, master, visiting PhD students also. So in the center, we have several lines of research, let's say big lines of research, like health and well-being, mobility and transport, culture and experience, industry, etc. And we are, I personally are in the line of mobility and transport, since I work in advanced driver assistance systems, autonomous driving, and also in the use of simulation for supporting the solutions of these problems. In fact, I like to say that I'm not that far from you in terms of personal life, since I was born in one place called Piedras Blancas, which is just 1.5 hours by car from you, very close to the Calar Alto Observatory that probably you know. And so I used to go before the pandemic around this area every year. So even I live in Barcelona, I was born here, and I think I'm the last person alive that was born here, because now this is an unpopulated area in the middle of the mountains. Okay, let's go for the talk itself. When you talk to regular people about autonomous driving, what they imagine is something like this, which is something like, I would like to go from Barcelona to the headquarters of DaSCI in Granada, and then I tell this to the AI of the car, and the car just bring me there, and in the meantime, I may be preparing this presentation. So I have 8 hours and a half inside the car, and I can do many things without attending the driving itself. This is what people think many times, but it's not the case. This is very far away. This is called actually in let's say classification from the Society of Automotive Engineers. What I was describing before is level 5. Let's say that car that you may know from the news, like Tesla cars and so on, are somewhere in 3, maybe close to 4, and not that far. They were in 2.5 or something like that, let's say. But nobody is in 5. This is far. This is far, because there are many issues to solve, not only technicals, but all kind of issues before having this such a super high level of automation. In the past, mainly before 2010, in my group, we were working in level 1 things, like which are known as advanced driver assistance systems, like pedestrian detection, lane marking, following, all these kind of things that many of them are today in some car models as additional functionality. And all this was done before deep learning, of course. So it was based on traditional computer vision and machine learning, like using specific features, using a random forest, all these kind of things. Okay, but at some point, as you may know, well, if you are very young, maybe not, but people that has more experience already, they know that around 10 years ago, it was a hard change in the way we were addressing computer vision problems, and we moved from this traditional computer vision and machine learning towards the deep learning, which has the advantage of being a model which is directly the algorithm that you want to develop. Before, we were like putting together several algorithms, doing partial things, and together they were doing what today can do a single neural network. And the point is that we have moved from handcrafting features to somehow handcrafting architectures of convolutional neural networks or any other deep model. Okay, but no matter in what kind of paradigm you were working, in all the cases, and this is already known for more than 20 years, in all the cases, we need supervised data. The difference between deep learning and previous methods is that deep learning requires much more data. With supervision, we were able to inject in previous models, because in previous model, if you have many data, it doesn't matter, because they were not able to improve from some point on. With the deep learning, you can keep feeding data, and hopefully the model will be performing better. Of course, there are non-supervised methods, but today they are not performing as good as when they are supervised. So the problem here is that in computer vision, but supervision is a nightmare. It's like if you want to detect pedestrians, then you have to draw bounding boxes, framing these pedestrians. If you want to assign a specific class to each pixel of an image for doing semantic segmentation, then you have to delineate all the objects of interest in your images. And while framing pedestrian can take a few seconds, if you are experienced, the delineation of silhouettes can take half an hour, or an hour and a half, depending on the complexity of the image. So this was a nightmare from the very beginning for us. So more than 10 years ago, more than 12 years ago, we decided that perhaps it would be a good idea to use computer graphics, video games, to generate synthetic data or data with automatic supervision. For instance, in this case, that was taken from the Half-Life 2 video game. As I said, more than 12 years ago, we were acquiring images and with automatic ground truth for the pixels showing a pedestrian. So we could collect examples and counterexamples to train our models. The point is that we were also able to do or to generate very weird cases like this that people sometimes was saying, okay, but why do you need this? Well, because in reality, you can find all kinds of things. So if you can control how this generation is done, this is a good point. And in fact, we were like training pedestrian detectors using synthetic data, and then we use these detectors with real data, and actually it was working pretty well. So we keep going in this direction. So later we were able to generate our own worlds. We were building a synthetic environment in Unity to generate ground truth like 3D bounding boxes for cars, pedestrians, and so on. Also to generate automatic ground truth like depth for depth estimation, or semantic labels, class labels for semantic segmentation, even for instance segmentation. We were able to automatically generate all this data without manual annotation, of course, and this was translated into a data set that we call it Cynthia, and has been used by many people doing all kinds of computer vision problems. We were able even to generate a sort of proxy of LiDAR data, not only images, with automatic class labels on these 3D clouds. But of course, soon, very soon, already like 10 years ago, we realized that the problem is that, of course, you train your models with synthetic data, and many times you have issues when these models are applied in real data, because there is a domain gap. There is a domain gap, and then you need to go for domain adaptation techniques that allows you to train with synthetic data, maybe unlabeled real data, or a few labeled real data, and then come out with a good model for performing in real data. And this is at the time we were proposing all these things, and we opened a bunch of possibilities that many people have been working on since then, which is a domain adaptation problem in computer vision. So along this year, we have been very active in this kind of intersection between computer graphics, computer vision, machine learning, deep learning, domain adaptation, all these kind of things, organizing a lot of workshops in international conferences, and proposing systems like Cynthia dataset I said before, or the most popular Carla simulator that all of we will see later in relation to our own work. Okay, So if you are interested, I did a paper some time ago summarizing what we did before the deep learning era about using computer graphics and domain adaptation for training computer vision models. But this was 4 models before the deep learning era. So once we decided to go for deep learning, so that we solve our tasks like object detection, semantic segmentation, localization, depth estimation, all this with deep learning, so that later we can provide information to some control planner, planner or controller to move a car. Then we were focusing still in the same kind of problem, but with new models, right? So one of the things that in which we are working in the last years is in semi-supervised learning problems, and in particular we have been applying one algorithm called training or a pattern of algorithm, more than algorithm. It's a pattern of algorithm for self-labeling images for a specific task. For instance, here we started with object detection. This means that we have a bunch of unlabeled real images, but we have also a bunch of automatically labeled synthetic images that we can make to like more close visually by using, for instance, GANs model, so that we go from the pure synthetic to the GAN model that is more closer to the, which is closer to the real data. And then with all these labeled from synthetic data and unlabeled real data, what we try to do is to self-labeling all the real data. For instance, here we have an example of how the training algorithm progress. We start like this, where the red bounding boxes correspond to manual labels that we use just to validate our methods, of course, because if you have already the manual labels, then you don't need to do self-labeling. So this is just for validating the self-labeling algorithms. So the red one is, the red one are from humans. So at the very beginning, using only the synthetic data, we have been able to detect some pedestrians, to label some pedestrians like this, but we have errors like this bike classified or self-labeled as a pedestrian. Here it's not possible to put the frame for the car and so on and so forth. But as our co-training method progresses, because it's a method that has cycles, we can see that in the last cycles, we get a very good result, like this green box here matching the red box, so the human labeling, and no false positive. Here we are able to label the car. Here this pedestrian also, which was very difficult at the beginning. And in here you can see how we were able to correct the initial result, that is this green here, which is just labeling half the car, until labeling the full car. So since this method was promising, we thought that keep working on semi-supervised learning was a good idea, because of course there are many unsolved problems. Like here, the human somehow guesses that this car that is just partially seen still continues here, but our algorithm is not able to move that far as the human. Or here, we label two bands, this one and this one. We label two bands as one single band, while the human was labeling only the closer band. So there are discrepancies between the method that we use and the manual labeling. But we have been still working on that kind of topic by applying the same idea to semi-supervised learning, to semantic segmentation. And in this case, the point is that we were able to self-labeling the popular cityscapes dataset until reaching a final score of 70 in the mean intersection over union metric, which is the standard metric to measure semantic segmentation. And this was, in fact, a state of the art, and I think it still is state of the art. So we were able to use only synthetic data and label it real images, and obtaining this result that is just 8 points behind the upper bound, which would be corresponding to have manually annotated images. So you can see here some visual examples. In the left, we have the results of only applying a model that has been trained only in synthetic data. In the middle is a first step of our algorithm, and in the right is the final result of the algorithm. So you can see how, for example, here there are errors labeling the sidewall. We improve it a bit, well, a bit, not quite a lot. And finally, we are even able to improve small errors that were remaining. And in here, you have the same. You can see how we can recover from all these errors that we would have by only using the synthetic data. In here is the same, but for other classes, like you can see here, there is an error labeling this big band, and the self-training stage is improving, and the co-training state improve it even more. And the same is the case here with cyclists and pedestrians. We keep improving the self-labeling over only using the synthetic images. And by the way, by doing this, we can also see that the humans are providing inconsistent labels also. For instance, in here, they forgot to label the traffic sign, sorry, the traffic light and the traffic sign. They didn't label it. So sometimes our algorithm is saying that in here there is a traffic sign, in here there is a traffic light, but it's accounting as an error because it's not actually in the human annotation. Or in here, you see this fence here is annotated as a single thing, while here the humans are delineating well the fence. So there are inconsistencies in this human labeling annotation. Another topic in which we have been working by using synthetic images is in monocular depth estimation. We have developed a method that is able to do the following. In training time, you can have synthetic images, and you can have images acquired from a camera, so that you can do a structure from motion from this camera to provide self-supervision for monocular depth estimation. So with this camera alone in training time, and with this synthetic data, we have been able to develop a method that in testing time performs monocular depth estimation. This is for those of you that are not familiar with this topic. The point is that usually what people do in training time is to use the LiDAR, which is in correspondence with the camera. So in training time, you need an expensive system also to collect the data and then train your model. And yes, then in testing time, you can use only one camera. So this is our method actually is performing pretty good in the international rankings. But anyway, the point is here that I wanted to enhance is that For training this model, we use sequences from a monocular camera and synthetic data where we can have the depth. This is the point, that in the synthetic data, we can have many frames with depth, because this is a signal buffer of the engine that you use for rendering the images. And also, of course, you can have the semantic segmentation, so that as we do, you can, for instance, force in training that some car, and that, for instance, the cars are more important than the floor, whatever you want. I mean, basically to give more relevance to one class or another during the training of the monocular depth estimation. So in here you can see examples. This is the depth estimation. The color tells you the distance, and this is a 3D reconstruction, like from another different view from the original one, in which you can see something that makes sense just because the estimation of the depth is good. If the estimation of the depth would not be good, or is not in absolute terms, but you would see here in this 3D view would be a crappy thing that doesn't make sense in 3D terms. You can see it here in a video. So we can reconstruct in 3D a sort of sequence from a different view, thanks to the estimation of the depth here. Okay. So more things. We actually tested the method in totally unseen images. It was funny for us to see that. That, for instance, if you look at here, you see that the system was able to perceive the dog as something. Of course, it doesn't know that it's a dog, but there is an obstacle there, and this was even without having any dog in the training images. But on the other hand, there are errors. For instance, you see here this horizontal barrier, but in here we don't see it. And in this case, we didn't have it any example in the training set, not even the virtual data. So if you see, once the barrier is moving, it could start to become more looking like a pole in a traffic light or a traffic sign or things like that. And then you see that that is detected, because these kind of things were in the training set. Okay. Okay, so far I have been talking about methods to minimize the data labeling when you approach computer vision, autonomous driving by, let's say, standard methods or a standard paradigm where you first of all perceive what is around the car, and then you provide this information to a system that do the planning and control. But there are other alternatives. This is what we call end-to-end driving, which is one case where you input the raw sensor data to a neural network, and the neural network directly provides the control commands for the car, like the steering angle, the braking, the acceleration. So in this network, there is not any explicit knowledge about what is a pedestrian, what is a traffic light, what is a car, nothing. So you only train this network by providing raw data. So in here, of course, the point is that you need to provide many experiences to the network so that it can learn. Why? Because in fact, we use imitation learning. So we collect a bunch of data from drivers or from a simulator with autopilot. And then from this episode, these examples of driving is what you use for training the network. So before going to see some examples, of course, there are pros and cons depending on the method that you use. If you go for the traditional, if you go for the traditional method where you first perform like visual tasks or based on other sensors and then you plan and control, of course, the interpretability of what is going on is easier. While here, this is pretty much a black box so far. Of course, there are ways of understanding a bit what is going on, as we will see in a while. But in general, I would say the interpretability is worse. But of course, in the traditional method, the data labeling is intensive because you need to do it for semantic segmentation, object detection. And if you change your camera to avoid domain annotation issues, probably you have to relabel part of the data. It's a nightmare at the end of the day, and the companies have a lot of people doing professional labeling because otherwise the labels are not with good quality. And in here, the point is, and this is the interesting part, is that we don't need any human labeling. The supervision for this network are signals from the own car, which can be automatically collected. For instance, to train this network, we need the steering angle, the speed, the acceleration, and the braking, but these are signals that you can acquire in your own car and synchronize with the acquisition of the images. So no manual labeling of images is involved. So the point is that you need to provide enough experiences, but actually this is also the case before in the other paradigm. Okay, since now we are talking about driving, of course, one of the things that we were experiencing is that, of course, we don't have to have a autonomous car and maintain an autonomous car is really expensive. And then we decided to use simulations, but all the simulators that were available were very crappy, to be honest. I'm talking about 6 years ago. So simulators in which you can control everything and do whatever you want, etc., were not good enough. So we were lucky to collaborate with Intel, and we developed what probably now is the de facto standard in simulation for autonomous driving in terms of open source simulation, which is the Carla simulator. Car Learning to Act is the name we gave to this simulator, and you can download it and use it with MIT license. It's not only that the code is open source and available, it's also that the digital content, the 3D assets, the materials, everything is also there for free. So you can use it. And this is because we have been sponsored along these years by different companies like Intel, Toyota, Research Institute, General Motors, Future Way, etc. Unfortunately, I have to say that all the companies are from the USA, no European companies, no Spanish companies. Even I know that many of them are using Carla for their own things. So I will skip this because this was about showing how companies can build on top of Carla. But I would like to say that, of course, one of the outcomes also of Carla is that there is the Carla leaderboard where we are putting together scenarios and situations, and is the place where people can test their own algorithms, their own autonomous driving stacks to see how these perform against others. I personally don't participate on this because it would be very weird, to be related to Carla and be participating in the leaderboard. But I know that many people is using this to evaluate their own methods. So coming back to our own research, we proposed it was 4 years ago or 5 years ago, I don't even remember, what is called conditional imitation learning, which is an end-to-end driving model, a neural network that is able also to accept high-level commands. Like when you are approaching an intersection, you can tell the network, now in the intersection, I would like to go to the left, or I would like to go to the right, and so on. Like when you are following yourself the Google Maps, for instance, and the Google Maps says, in the next intersection, turn to the right, something like that. Notice that we are not saying, in 10 meters, there is an intersection and you have to turn left. No, we don't know how far are we from the intersection. It's just that we know that we are going to find an intersection because this is in the topological map. And then once we are there, we will have to turn one way or another, or just keep going straight. But we don't know the distance. This is something that is not part of the model. Okay? And well, of course, we did several variants of this model, like using not only images, but also depth from monocular depth estimation to do a kind of fusion, which was working pretty well. Actually, these papers have been very well accepted. I think that Carla has more than 2,000 citations in Google Scholar, and the conditional imitation learning, the first paper, has more than 600, I think. So many people is following these kind of ideas nowadays. And here you see an example of what this model is able to do. You see that it's able to stop in red traffic lights and pedestrians. But the point here is that the system doesn't know what is a traffic light, doesn't know what is a car, doesn't know what is a pedestrian. It's just that it learned the behavior from the experiences that we provided during training. You see here, it was turning to the right now, for instance, just because we tell to do it. Of course, you can see that there are errors, and this is why we keep working on that. And in fact, there are intermediate solutions, not only pure end-to-end driving, as we will see in a moment. So these days, in this end-to-end driving, we are focusing more in specific scenarios, like we can define in Carla specific scenarios, like now it will appear a bicycle from the sidewalk, and then you have to stop. But you see, this is the kind of visualization that we use now to understand a bit more what is going on in the network. Here, let's say that the red means that the network is paying more attention to that, and the blue is no attention at all. So you can see how it's looking to the lane, and then when the pedestrian was there, sorry, the bicycle was there, it was moving the attention to that. You can see it again. And now it keeps driving, looking at the lane. Okay, now this is a project, a real project that we are doing in the Pyrenees. It's like very close to Andorra. Also, it's like 1,500 meters of altitude or something like that. And it's like 3 hours and a half driving from our lab. You can see here, this is a road in the mountain. And then the idea here is to do a sort of tram in the mountain. So a car that goes and returns in a given road that is very unused, and the people that is living around there don't have any public transport system. So we investigate if it is possible to use autonomous car in terms of cost and all and safety and all these things in these kind of places. So the point is that at least the road has asphalt, that's for sure. There is a lot of vegetation, there is not almost traffic, and so on and so on. The point here is that it's really narrow. It's really narrow, and it's difficult to make it bigger. In fact, it's not possible. We cannot do it because to the left, well, depending of course in the driving direction, but in this case, to the left we have the mountain, so the walls of the mountain, and to the right we have the river. And we don't want to do any intervention in this nice place, just to use what is there. As you can see, this is I was there with my car. There is very few space for errors, you know. Then what we did is to build the place in Carla, because we needed to do a lot of testing. Let's say it's not only testing a specific model, it's also to figure out what is the best model. So at the end, we will have the car only a couple of months to do the real demos. So we needed to do a lot of research before going to the real car. And this was totally impossible if you don't have a simulator. If you are only checking your results in images, this is a problem. We already saw it in a paper that open loop evaluation has nothing to do with closed loop evaluation. And here we need to test the car in closed loop. So it's driving by the AI, and then the next images that the car is going to see are depending on this motion. So it's a closed loop. So these are just an example. Let me put this was the beginning of the route, which is 4 kilometers. Maybe I can put the last part also. So this is arriving to the other extreme of the route. You see that we have here the river in this case. This is more or less, I think this area is like 4 meters width. I don't remember exactly now, but not that much. So in here we are able to change the vegetation depending on the season. We are able to change the hour of the day, so the shadows will be different depending on the hour. We can put animals in the middle of the road to train the system to stop. We can put people, we can put other cars, all these kind of things. And how we did it? Well, basically we were using GIS information that is publicly available from this area, so that by taking this information from the CNIIG, which is a Centro Nacional de Información Geográfica, we are able to ingest this information in an intermediate application that we use to generate a standard for generating driving scenarios, which is called OpenDrive. This is injected into Carla, and also we have our own 3D digital content that we populate automatically after injecting these kind of mountains and roads without test tool. Then we can populate these mountains and roads with our own assets, materials, and all this to obtain what we have been seeing before. This is a semi-automatic process, it's not fully automatic. So with this done, we were testing several approaches for the autonomous driving. Basically, we are performing semantic segmentation, monocular depth estimation, and 3D object detection. With this, we generate a bird's eye view, and then we have two options that we are evaluating, which is one of them is to know what are the waypoints that the car has to follow by using a sort of ad hoc algorithm based on the road borders, or not using any ad hoc algorithm, but imitation learning network that knows which should be these waypoints by imitating the behavior of the real drivers, or in simulation the behavior of the autopilot. For instance, in this video, this is a selected piece of the scenario where in this case the car is driven by the autopilot. That means that this autopilot knows everything about the world. It knows where is the road, it knows where, if there is an obstacle. All this is known by the autopilot. So it can perform a perfect driving, and we can collect a lot of episodes of driving by changing different parameters of the environment and the obstacles and so on. And with this data is used to train all these models I was mentioning. And now what you see is actually driven by the AI that we will deploy either directly or after adaptation to the real car. So in this case, the car is not driven by the autopilot, but by a vision-based AI that has been trained to drive. Okay, because we were able to generate this virtual environment, we after some, let's say, cooking, because it's a bit of semi-manual process, we have been also able to generate more photorealistic images for the training of the models. And these photorealistic images cannot be used so far for real-time simulations because each image can take minutes to render, since this is physics-based rendering. But you see, we can have this kind of images. And the idea is that, of course, these images with different variations come with the corresponding ground truth. And then we can minimize the number of annotations that we will need to develop our models or to adapt our models to the real car and the real environment. So we have been also changing a bit the topic, but still working with photorealistic images. We have been also working in surveillance, video surveillance applications, because sometimes there are critical places where you don't detect problems until it's too late. Like here, that it was almost a crash with a pedestrian, with another car, but if it actually doesn't happen, then you don't know. But if you train models to detect these almost accidents, then you can figure out which intersections or places in the city may require some action to avoid future accidents. So because the world is so complicated, you see here, I took this from the internet. One guy in the well, let's say that is not following the proper way of moving in a traffic situation. Then we would like also to generate photorealistic videos. This is more complicated. Here there is an example where I have just, I'm sorry, I needed to hide the car maker. But you see, it's the same situation, but with different actors. And so in this case, we were having real images and we were putting photorealistic actors to move in these realistic images. So that you can have examples that were not there in the images that you acquired for training your models. So for instance, you have an example, one frame from the previous videos. This is a real person, real cyclist, while this one is not real, it's just fake. But you see that we have here the shadows, we have the projection in the car, and yeah, it's relatively well integrated in the image, but this is not trivial. To automatize this is very difficult nowadays, since you need to synchronize time. Also, if they imagine if this person is working and there is the border of a sidewalk, it needs to do the corresponding motion that don't look too weird and all this. So it's a very interesting topic, but it's not easy to tackle. So that was all. I think it took almost 50 minutes for me, but I hope this is okay. So that and my presentation that I hope you were able to follow. Thank you very much.
Well, Antonio, thank you very, very much for your talk. And now it's time for questions. Any question from the audience?
Hi.
Hi.
So thank you very much for the presentation. I had a question about when you talked about semi-supervised learning. So if I understood it correctly, what you said is that like you train a model in the simulator and you use that trained model to to label the data from the real world. And also you talked about the GAN, so I didn't understand that very well.
Yeah, this is because I was a bit fast. Now, let's say that in this context, we are talking about traditional computer vision tasks, like detecting pedestrian, doing semantic segmentation, all this kind of tasks. So these are, in here there is no actual driving. These are processing the images to later provide this information to a further stage of the whole system that can make the car to move, actually to move. In here is just about detecting the content of the images. So what we did is to use synthetic images that are already a data set. It's not like when I was showing the examples of Perla, this is real time. This is changing every time you run the experience. It may change a bit if you don't fix everything. But in here you have a data set that is generated from a video game or whatever other system that you may have to generate synthetic images. In this case, we were using our own data set, the Cynthia data set. And then once you have these synthetic images, the best thing that could happen is that you train, for instance, a pedestrian detector, you apply it in real images, and it works. But doesn't happen. It never happens. There is always a, let's say,
Well, I think we have lost the connection, yes. Let's hope he can reconnect soon. Can you hear me? Or
Yes.
Okay.
Yes.
Okay, thank you. Because I was afraid that I was also losing my connection.
Maybe he's unaware that he's not connected right now.
I'm not sure, because even prior to this talk, he was telling me that the connection from his side was not very good. So I think, in fact, I think he went out from the meeting. I hope he's going to reconnect now. I hope.
I hope too.
Yeah.
Se ha caído, ¿no?
Sí, sí. Bueno, le voy a enviar un email.
Sí,
Sí, enviar un email a ver si a lo mejor pues, sí, está con el portátil y se ha quedado sin batería.
No vaya a ser que esté hablando él solo.
Ese es mi miedo, que siga él hablando.
Se le ha cortado algunas veces durante la reunión un poquillo. No sé si se ha dado cuenta.
Sí, sí. Bueno, esto luego habrá que editarlo, Eugenio. Estos momentos. Fuera de la charla. O sea, le voy a enviar un correo.
Bueno, ahora que sobre todo tenemos aquí a doctorandos.
Okay.
Sorry,
problem.
yeah.
No
My
problem
internet was down, so I'm using my mobile phone. Let's see if I can continue the explanation.
Yeah, sure. Go ahead, please.
Okay, so the point was that you have a bunch of real-world images that don't have any labels, a bunch of synthetic images that have labels, but for the thing that I'm talking about now, we don't need these labels. We only need the images, the RGB images. So you can train a GAN, which in this case we were using the popular cycle GAN, so that you transfer these synthetic images to look more similar to the real world images that you are working with. Okay, so this is a first step. With this,
that would be like domain adaptation, right?
Yeah, it's a first. It is. It's a first step in the documentation, but this is not enough. With this, you can improve, but it's not enough. And then what we do is to run from these transformed images and the real ones that are totally updated. But you know, the point is that this GAN thing only change a bit the looking of the pixels, but don't move the pixel, because otherwise the synthetic ground truth will be useless. It will not be really a ground truth if the GAN is just kind of moving the things in the images. So from this, you can train an initial model. And then from this initial model, you can run your semi-supervised learning, in this case, a co-training method that starts failing, but after some cycles, where in each cycle, basically what is done is to detect or labeling in the unannotated images, real images, labeling part of the image or up to some point with errors, of course, but you can use these self-labels to retrain the system cycle by cycle until converge.
So basically, what you do is that you transform the synthetic images to more like real images, and then you train a model over these like new images that you have the label from the simulator, but you have the data distribution of the real world so that they look more like. And is this enough?
With this co-training method, we were reaching. I don't have here the numbers, but we were not far from the upper bound, which corresponds to train with real images. But I could say, let me say two things. Not always is needed to do this GAN thing. For instance, in the semantic segmentation application that I was talking after this slide, we didn't. It was not needed. And regarding it is enough, and not because there are these kind of things that we are not yet able to solve. You know, the human annotator, for instance, was guessing that this car, for instance, this black car ends here, but our system was like saying no, it's ending here. So it depends how far is the manual from the self-annotated labels. You may be doing well or not, but it's not totally, it cannot be done yet totally automatically, the self-labeling with our method. Of course, the companies maybe have some better methods, but we don't know them because these are secret, of course. This is one of the important things in the companies for labeling data.
Nowadays, like with the more realistic environments, for example, like Unreal Engine 4 and all of that. So is this still necessary or like no longer?
Yes.
Because
yes,
I suppose if you do physics-based rendering and all of that, that's better than the GAN, what the GAN can achieve, right?
No. It's better, yes. Not sure if I would not. It's true that we are removing the GAN by using that, but still is not enough. I mean, even if it is more photorealistic, it's not enough because, and I want to clarify this. If you take images from one real world camera, you train the model with these images, and then you test this model in images coming from a different setting of camera, but still a real world camera, but it's a different camera, you still may have this dominantation. And these are two real world cameras. Both images or both sets of images are real world images. So it's not, the dominantation is not an issue of synthetic to real. It's an issue of sensor to sensor, where synthetic to real is a special case.
Okay, so thank you very much.
Any other questions?
You're welcome.
More questions from the audience? No? Well, I have a question for you, Antonio. And well, in fact, I have several questions, but I hope that somebody is going to ask more things in any case. Related to what people understand by autonomous driving and how far we are from a SAE level 5 car, in your opinion, what is the main technical issue that prevents from getting there? I mean, what is the bottleneck? We are talking about a car where no human intervention is required at all, that works on all kinds of surfaces, all over the world, all year around, in all weather conditions. From your point of view, at a general level, what will be the bottleneck to get there?
I think the bottleneck now is to have a protocol which is good enough for testing every autonomous driving stack, so that you say, if you pass this protocol, then we are in the safe side of the equation. Your system is good to drive. We don't have such a testing or protocol that ensures that so far, and it's not trivial, because in the real world there are many crazy things. At the end of the day, it's not about the usual driving. Maybe you will perform perfectly 90% of the time, but then there is this remaining 5% of weird cases that you did not experience where you were testing the system, and then this may be a source of issues and of big problems, because at the end of the day, the human drivers not only know to drive, we know about everything in the world. If we suddenly see, I don't know, an elephant in the middle of the road, we say, what? Oh, it's possible. This is the AP7. We are in Europe, but there is an elephant in the middle of the road. But an autonomous car knows a closed world. Yeah, then sometimes it may be difficult to figure out what to do in some cases, or even worse, to know that it doesn't know about what is being seen. So the capacity to say, I don't know. And so since I don't know, the best I can do is just to stop or move out of the traffic, because in here it's happening something that I don't know. This I don't know is not trivial.
Okay, thanks a lot. We have a question. Natalia, please go ahead whenever you want. We cannot hear you, Natalia.
Hello. I'm sorry.
No problem.
Sorry.
No problem.
Thanks for your talk. It was very, very exciting. I'm having a lot of questions, but I'd maybe try let's see. I'm wondering, it seems that you use some kind of privileged information framework, right? Like sometimes you train with more modalities and then you test with some less modal. I mean, you assume that you will not have all modalities on which you train your system. So is this related somehow with the privileged information framework of BAPNIC? I don't know so much about it, but I've been wanting to learn, and I'm not sure if it's related.
No, let's say, for instance, maybe let me go for one specific. Yes, here. In this video that is happening in simulation, of course, this car here. Well, 1 second. This car here is being driven by autopilot. And in this case, autopilot means that it has access to indeed all privileged information of the simulation, like where is the road exactly, if there is some obstacle in front, all the information needed to drive. But this is because we need to collect data for training. So what kind of data is collecting this car here? Is collecting images, is collecting also the steering angle, the acceleration, and the braking of the car. Because in here we are training an end-to-end driving model based on imitation learning. So this is why we access the privileged information in the simulator to do a perfect autopilot. Then the question is, okay, but then how do you do this in the real life? Okay, for instance, if this were, rather than imitation learning, this were reinforcement learning, the way of learning this would be like crashing 100,000 times, which is something that we cannot do in the real life. Okay, but in here, because it's imitation learning, in real life, what we would do is to have a fleet of cars with cameras and collecting the images and the steering angle, the acceleration and the braking synchronized with the images. So it's something that can be indeed done. But of course, here the problem is that you need many driving examples to make this work well, because we are not giving the model any explicit information about what is a pedestrian, a car, whatever. And this is why you need hours and hours of examples driving. This is why in this real life project I was mentioning before, which is just, is this one, rather than using a pure end-to-end driving thing, the input to the imitation learning are semantic segmentation, depth estimation, and 3D object detection, because then we need less experiences to teach the imitation learning to drive well. So the privileged information was done in the simulation for simulating a real driver driving well. And as a curiosity, is important that in these simulations, you also train the model to recover from errors. Like if you were a real driver and then you are unattending the road, you start going to the right of the lane, for instance, and then you recover. You have to teach this also to the system. Otherwise, if there is some issue, it will not recover from this issue.
Okay.
And for doing that, we need also privileged information in the simulator.
Okay, thanks. Because, yeah, because it seemed to me like the imitation learning somehow it's a bit like autopilot-like tasks, right? Things where you kind of let your agent go along. But I'm wondering if this training, imitation learning, or behavior cloning could also be used or together with the cyclotron approach to not only create like domain adaptation data, but also to maybe infer, is the car parking now? Is the car now driving in a dangerous area? Like, I'm wondering if this could be more used for action recognition or something more interpretable.
Yeah.
Or actionable.
Yeah. Actually, you can. I mean, in our lab, we kind of like to research on the extreme cases, like pure end-to-end driving, what can be done. But of course, you can find intermediate solutions where things are probably easier to tackle. So yes, what you say is doable. For instance, one of the things that we are doing these days is to see if we are training in simulation end-to-end driving model, pure end-to-end driving model, where the input is the RGB image. How can we move this model to a real car by doing the domain adaptation, which means not only adapting the images themselves or the features extracted from the images, but also the own control of the car, because one thing is how you control a car in the simulation, and another thing in the real life, where you have wind, you have frictions that you may not have in your simulator. There are many other physical variables that you need to adapt.
Yeah, because I also saw, like in the example you put to learn from, let's say, cartoon image from a real image. Can you manage to make this in a video setting or just in still images? And if you can you still obtain kind of the privileged information behind the sensor?
What? Sorry, what? Do you remember what?
I think the paper you show, it's a screenshot that looks really nice, saying training my car to see using virtual.
Yes.
Where you have the video game and the photo. I'm just wondering if this could be done the same thing you're doing to drive for controlling face expressions. And somehow,
yes.
once you map the domains, if you could obtain back the actions of the control.
I think it's not in what I'm working, but I know that there is people that is training models by using this kind of faces in real in video games. Actually, one of the first applications of this kind was the Kinect. The Kinect was trained on synthetic textureless depth images of people. So Kinect was an example of working well from synthetic data to real data.
Okay, thanks a lot.
You're welcome.
Thank you very much. I think we have time for a last question. Guillermo, please go ahead.
Yeah, thank you. First, thank you for your talk, Antonio. It was really interesting. I have one question. It's in the barrier between the ethical and the technological. As you said at the beginning of the talk, the technological development have come from the custom or human made feature extraction to a fully automated and end-to-end models. We are seeing this phenomenon as well in many other areas on the deep learning and machine learning. So the thing is, I guess we are gonna see sooner than better that a fully autonomous train in an end-to-end manner car is available, but this is working as a black box is a lack of control. Right? We are letting go much of the control we had when you, for example, put the two alternatives between a border of the track alignment or fully autonomous end-to-end driving. So the thing is, do you think the limit we are going to face once we have this kind of cars that can drive successfully autonomously but in an unsupervised manner, we are going to face a legal limit because we cannot perform an exhaustive validation on every possible scenario in the road. So do you think we are going to assume, as we do, for example, with planes, meaning that we might be afraid of planes, but we assume that they are more reliable than cars? Do you think that we are going to settle for autonomous car being more reliable than people, even though we have not control in many areas that a human could solve better?
Well, let's say that this is not an easy question to answer from me, because it's probably better known by people in the industry that sometimes don't share all the internal development. So I don't know how far is this, but let's say that yes, one thing that is known is that we cannot wait until the autonomous cars are perfect. Mm-hmm. It's better to have good ones, but not perfect, and deploy before than after. There are numbers, there are some papers that are done this study, and they show that this will save more lives if we deploy sooner something that is reasonably well behaving than just if we wait for a sort of perfect system. Mm-hmm. So this is one thing. The other thing is that this question is different in Europe and the US and China. In Europe, there are a lot of regulations. So there are European projects that are trying to set up this legal framework also. So I think that until the legal is not totally clear in Europe, probably we will not see this deployment of cars. In the USA, probably it's going to be different. They will do some, of course, some legal points, but maybe they are not going to be as restrictive as in Europe, so that they can start before. And you know, the sooner you started, the sooner you improve your systems. So I think that this is going to be interesting for sure to see how Europe, China, Japan, and the United States address this problem of the legal things. But my feeling is that in Europe, until the legal things are not super clear, they are not going to allow this kind of deployment of full automation. But still, we are not close to the full automation in technical, from the technical part. So they have time enough to do it.
Yeah.
So let's see.
Okay, thank you very much.
Okay, so, well, if you want, we can stop here. We thank our speaker again. Thank you very much, Antonio, for accepting our invitation.
You're welcome.
For this very nice talk and for all the questions and all your answers to these interesting questions. And I think we can end here this seminar. Thank you very much, Antonio.
Okay, thank you to you for the invitation and have a good day. Bye.
Bye-bye.